Okay, so now we're going to keep talking about iterative methods for solving systems of linear equations, and in particular we're going to talk about the Gauss-Seidel iteration. So as before, if you're looking for ax is equal to b, I'm going to consider a decomposition of a into n minus p. And when I do that, I can write down an equation nx is equal to px plus b, right? And so you can think of this as a fixed point equation that x is equal to n inverse px plus b, all right? And again, this is a fixed point equation. And associated with that is a fixed point iteration, xn plus 1 is equal to n inverse pxn plus b. Okay, so with Gauss-Seidel, what happens is that n is the lower triangular part of it. So for Gauss-Seidel, right, n is the lower triangular part of A. Okay, so let's see what happens. Okay, so we had an example from before where A was 9, 1, 1, 2, 10, 3, 3, 4, 11. So I'm going to write this as 9, 2, 10, 3, 4, 11 minus minus 1, minus 1, and a minus 3 here. So the fixed point iteration is that xn plus 1 is equal to 9, 2, 10, 3, 4, 11 inverse applied to b1, b2, b3 minus x2 n minus x3n. Okay, and then minus x3n here. Okay, so let's try to solve that. Let's see what you get. Okay, so for the okay, so I'm going to actually move this to the left hand side, and I get the following. I get 9x1 n plus 1, 2x1 n plus 1 minus, plus 10x2 n plus 1, and then 3x1 n plus 1 plus 4x2 n plus 1 plus 11x3 n plus 1, right, is equal to b1 minus x2n minus x3n, b2 minus x3n, and b3. Okay. All right. So I can solve for x1 n plus 1 is equal to Okay, 1/9 b1 minus x2n minus x3n. Okay, and then I'm going to move this entry to the other side, okay, and then divide by 10. So x2n plus 1 is equal to 1/10 b2 minus 2x1 n plus 1 minus x3n, and then x3 n plus 1 is equal to 1 over 11. So I move these two entries to the right. I get b3 minus 3x1 n plus 1 minus 4x2 n plus 1. Okay, all right, so this is the Gauss-Seidel method. All right, so hopefully it's clear now that it still satisfies the same fixed point equation as you would expect, right? So the fixed point equation in question is that x1 is equal to 1/9 b1 minus x2 minus x3, x2 is equal to 1/10 of b2 minus 2x1 minus x3. Sorry, there's a I think I made a mistake. So that's 3x3. Okay. And then x3 is 1/11 b3 minus 3x1 minus 4x2. Okay, so it's easy to convince yourself that the fixed point of this iteration is exactly still a solution of the original system of linear equations, which I've manipulated in this way, right? And except that with a traditional fixed point iteration, everything on the right is the nth value, everything on the left is the nth plus first value. So here with Gauss-Seidel, it's a little bit different because I'm looking at the entries sort of row by row, if you will. So for the very first row, right, I get, you know, it's like I don't know, it's like the new values, it's like for x2 and x3, so I use the older values, which the nth iterates. But now in the second row, right, in the second equation, I have x1. x1 I know an updated value, so I'm going to use the updated value here instead. But x3 I don't know the updated value, so I use the older value. And then for the third equation, x1 and x2 both have updated values, so I use that instead. All right. So that's the main distinction. It's like between Gauss-Seidel and Jacobi iteration, right? Is that they're both trying to solve this type of fixed point equation through some sort of iterative scheme. But with Gauss-Seidel, once you've computed a new value, you use that in the other components of the iteration. Okay, so that's the main distinction. So hopefully it's quite clear when I write it this way. You know, it's like that you're using the new iterate when you can, right? And when you move it to the right-hand side, you get essentially the same equation. But again, it's like whenever there's a new value, you use that instead. Okay, so that's the Gauss-Seidel method. Okay, so you might imagine that there's sort of a variant of this where instead of the lower triangular matrix for n, it's like use the upper triangular part, and you get something very similar, except that now, you know, it's like the equations sort of get numbered from the bottom up, right? So you sort of think of using the bottom equation first. And then once you've computed the x3, for example, it's like you use the value of x3, the new value x3, in the second to last equation, and you sort of go backwards. Okay, it's a little bit like forward and backward substitution, because of course intuitively that's what you're doing here, is some sort of forward and backward substitution. Okay, so all right, so let me just stop here for now. It's like, and then the next thing we'll do is to write down some pseudocode. It's like for both Jacobi and Gauss-Seidel. Okay, but let me just stop here for now.